Hi everyone, we are from the group The Cargon Agents, and in this video, we will be presenting the paper titled WebRL Training LLM Web Agents via Self-Evolving Online Curriculum Reinforcement Learning. This paper focuses on improving the ability of large language models, or LLMs, to act as autonomous web agents. In simple terms, a web agent is an AI system that can interact with websites by performing actions such as clicking buttons, typing information, searching, scrolling, and completing user instructions. The main goal of this paper is to train the open source LLMs to become more capable web agents rather than relying on the expensive closed source models. Moving on to the background, LLM have already shown their strong ability in language understanding, reasoning, and knowledge generation. However, recent research is moving beyond simple text generation. The focus is now shifting toward agentic AI, where an AI model is not only answering questions, but also planning, making decisions, and taking actions in an environment. This is important because many real-world tasks are interactive. For example, searching for product information, managing online orders, or navigating a website requires the model to understand the web page, choose the next action, and recover when something goes wrong. This is where the deep reinforcement learning becomes useful. Through reinforcement learning, the agent learns by interacting with the website and receiving feedback based on whether the final task is completed successfully. Next, I will pass the presentation to Huixin to discuss the motivation behind this paper.
Hi, I'm Chuijin, and now I'll be moving forward to the problem and motivation in this paper. Existing web agents mainly rely on proprietary LLMs like GPT-4, which are powerful but expensive to scale. Meanwhile, open source LLMs lack sufficient decision-centric training data for effective web navigation. As a result, training capable open source web agents in online environments become challenging. First, online environments like Web Arena only provide limited scalable training tasks, which restricts continual learning. Second, web tasks have sparse feedback signals because task success is difficult to evaluate. Lastly, online exploration causes policy instability and catastrophic forgetting. To solve this, the paper proposes WebRL, a self-evolving online curriculum reinforcement learning framework. Implementation details will be continued by Kaiwen.
Thank you, Amber. I'm O. Kaiwen. I will be talking about the methodology of this research paper. The actor and LLM policy generates web action from HTML instructions. It interact with the web arena simulator. Reward is sparse 0 or 1 only at the final step. The ORM scores task completion with a binary yes or no. File tasks get rewritten by GPT-4o into new variants. The critic filters by difficulty scores between 0.05 and 0.75. Filter experience go into the replay buffer. Then the next curriculum phase begins. So why not PPO or DPO? PPO needs fresh-on policy rollouts, too expensive for live web pages. DPO needs pairwise preference, but our feedback is binary only. WebRL uses MSCE laws instead. Beta log policy over reference equals the advantage. Regress the policy directly to match the advantage. Is off policy. All trajectories are reusable. The KL terms anchor the policy preventing forgetting across phases. In evaluation study, replay is the most critical component. Without it, if features overrides prior knowledge, all three parts reinforce each other. Remove one, the system falls apart. So I'll pass back to Amber. Thank you.
Thanks, Kaiwen. Now, WebRL introduces four main innovations for training web agents. First, unlike DGRL, which uses fixed task sets, WebRL uses self-evolving curriculum learning to generate new tasks from failed attempts and progressively improve through trial and error exploration. Second, to solve sparse feedback problems, WebRL introduces an outcome-supervised reward model, or ORM, which automatically evaluates whether tasks are successfully completed, replacing expensive GPT-based evaluation. Third, WebRL addresses policy distribution drift using a KL divergence constraint between the current and previous policy, reducing catastrophic forgetting during online reinforcement learning. Finally, WebRL improves replay stability using actor confidence filtering, where only useful successful trajectories with moderate perplexity are replayed for training. And that's all for me. Thank you. Next, we are going to talk about the dataset used in this article. The paper used Web Arena and Web Arena Lite. These are benchmark environment for web agent, where the agent can interact with website to complete user instructions. The environment includes 5 website domains, which are Map, One Stop Shop, GitLab, Reddit, and Content Management System. This domain tests different web agent abilities, such as searching for information, navigating pages, managing content, and completing shopping-related actions. Web Arena contains 812 instructions, but the author used Web Arena Lite for evaluation because full testing is costly. So they used 165 instructions as test case and 1,186 training sample for initial training. Each training sample contains an instructions, a trajectory, and a reward function. For experimental setup, the model first undergoes supervised fine-tuning using Web Arena Lite, demonstrating trajectories. After that, WebRL further trained the agent through reinforcement learning in web environment. The main evaluation metrics is success rate, which measures the percentage of tasks completed successfully. Now I will pass to Xiaoshen to complete the presentation.
Thank you, Yanli. Now, I will present the main quantitative findings of this paper. The main results show that WebRL significantly improves the performance of open source LLM web agents. According to the table, the best performing model was Llama 3.1 8B trained with the WebRL, achieving an average success rate of 42.4%. This outperformed all baseline methods, including prompting-based approach, such as GPT-4o, imitation learning methods such as SFT, and even another reinforcement learning method called DGRL. WebRL showed especially strong performance in difficult tasks like GitLab and CMS, achieving 46.7% and 54.3% respectively. Compared to imitation learning methods, which often repeat actions and get stuck, the WebRL uses reinforcement learning to optimize long-term rewards, leading to better decision-making. In addition, by comparing 8B and 70B, WebRL scales effectively to larger models. When applied to Llama 3.1 70B, the performance increased further to 49.1%, showing strong scalability. Finally, the error analysis shows that WebRL reduces problems such as getting stuck midway, stopping at the wrong page, and failing to recover from mistake. This indicates that WebRL produces more robust and reliable web agents. Overall, WebRL significantly improves the performance of open source LLM web agents. That's all from my part. Next, I will pass it to Yanli.
Next is the critical analysis. WebRL has 3 main strengths. First, it improves open source LLM web agents, reducing reliance on expensive proprietary APIs. Second, its self-evolving curriculum reuse failed tasks to generate new tasks, so the agent can improve progressively. Third, the ORM generates success or failure feedback, while the replay buffer and KL constraint updates help reduce the forgetting and make training more stable. However, WebRL also has limitation. It is evaluated only on 165 Web Arena Lite test cases, so real-world generalization is still uncertain. It also depends on GPT-4o for task generations and filtering, and the ORM may give wrong labels. The main assumption that is generated task and Web Arena Lite result can represent real web agent abilities. That's the end of my part. Now I will pass to Huishan.
Thank you, Yanli. Good day, everyone. I'm Wang Huishan. Moving on to the next part, I will share our insights into the significance and real-world impact of WebRL. From a real-world perspective, WebRL-style agents can support many practical tasks, for example, online shopping, website navigation, data retrieval, customer support, content management system, and also online workflow automation. The biggest impact is that WebRL reduces the dependence on closed source models and helps open source models become more capable in web-based tasks. However, some limitations still exist. Firstly, the reward model may not always judge the task success correctly. Besides, the real websites may change their layout from time to time, which may affect the performance of WebRL agents. Therefore, the system may still require many interactions and training resources. Most importantly, the privacy and security issues must be carefully considered when agents interact with real websites. Lastly, to conclude our presentations, this paper introduced WebRL, a self-evolving online curriculum reinforcement learning framework for LLM web agents. The key idea is very simple. Instead of only teaching the model from fixed demonstrations, WebRL allows agents to learn from the interactions, failures, and progressively harder tasks. The paper demonstrates that this approach can greatly improve open source LLMs, making them more capable for completing the real web-based tasks. That's all for our presentation about this paper. Thank you for listening and feel free to ask any questions.